Okay, so here we have a little kind of flow chart that you can actually, there's a website for this one right here, but there are a variety of these different types of little flow charts that are very useful, and some of these mass or particles to moles kind of conversions that you have to do commonly in chemistry, as well as when we start talking about gas laws, where you can use Avogadro's molar volume for a gas at standard temperature and pressure. That may sound totally foreign at this point, but that's okay. You will do that a little bit later. But these kind of little flow charts can kind of help you out a good bit. So if you can have find you one online, and or modify it to make sense more to you. But it tells you how to, if you want to go from mass, say in grams, to moles, which we're talking about the amount of substance. It tells you that in order to do that, you have to use a factor of 1 mole over the molar mass. So in other words, if you want to go from mass to moles, you divide by the mass in grams per mole. So you divide that by the how many grams it is. Or if you want to go from moles to grams, you have to multiply by the molar mass. So this kind of gives you a conversion factor for that. And also to go from moles to representative particles, which it could be a representative particle, it could be an atom, or it could be an ion, so it's an atom with a charge. It could be a molecule, if you want to talk about that as a representative particle, or sometimes what you might refer to as a formula unit. Actually, typically those four are the representative particle types that are used quite frequently in chemically chemically involved calculations. So when we do these kind of stuff in chemistry, we'll use these quite a bit. So having something like that probably be very beneficial to you. And you can modify a little bit as to how you make yourself some notes in within it to help you out. But I'm going to be referring to this particular part of it through the next part of this part of the lecture video. So I'm going to move on through some parts of the notes, and I'm going to start with calculating molar mass. So there are several examples, textbook examples of calculating the mass of 1 mole of a substance. So one of the questions I might ask you to do is calculate the molar mass of a substance, and early on I'll give you a formula, and then later you'll have to tell me the formula and the molar mass and stuff like that, just based on its name. So you'll have to be able to go from a formula name, compound name, to a formula, and come up with a molecule like this, a molecular formula, a formula unit, whatever you want to call it. So this is for ethanol, and I've given you the formula for ethanol right here. It contains carbon, hydrogen, and oxygen in the molecule. And so I went to a periodic table, which you should have access to a periodic table, and I've just pulled these elements off the periodic table. So their atomic number, their symbol, the name, and the weighted average atomic mass for each of those elements. In order to do that, calculate the molar mass. You want the mass in grams of 1 mole of an element or a compound. So if we look at this, we have our 3 elements, carbon, hydrogen, and oxygen. And then I need to go to my formula, and I want to see how many of each type of atom I actually have. So I go up here, there's 2 carbon, so quantity of 2. Hydrogen, I want to count all those. There's 3, there's 2, and there's 1, so 6. And there's 1 oxygen atom. So in a molecule of ethanol, a single molecule, there are 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen atom. And then later what we'll talk about is in a mole of ethanol, there are 2 moles of carbon atoms, 6 moles of hydrogen atoms, and 1 mole of oxygen atoms. So here we'll take our information from our periodic table, and we see that carbon has a weighted average atomic mass of 12.01 atomic mass units, or 12.01 grams per mole. Our hydrogen is 1.008 grams per mole, or atomic mass units. And our oxygen is 16.00 grams per mole, or atomic mass units. Then I just really extended mass contribution. I just multiply the quantity times the mass off the periodic table. So I multiply 2 times 12.01, I get 24.02. And then 6 times 1.008 is 6.048. And then 1 times 16, well, that's just 16.00. So then I just add that up. So when I do that, that's 8 and a 6 and a 0. Bring down that. And then add that up, and I get 46. Now, if I want to report that to the proper number of significant digits, if I look at my numbers here, when I look at these, this had only 2 decimal places, and this only had 2 decimal places, and this had 3 decimal places. When you add or subtract numbers that are these measurements, then you must round your answer to the fewest number of decimal places from any of the things that you're adding together. So the fewest number of decimal places is 2 decimal places. So there's my second decimal place. So really, if you want to report this molar mass as an answer, like right here, calculate the molar mass of ethanol. So your reportable answer is 46.07, because that 8 makes that 6 become a 7. And then you would put units of grams per mole. You might also sometimes see it written, if this is not your final answer and you're using this as just part of your calculation to reduce your rounding error, you may show that as 46.06 and then write your 8 as a little subscript number down here. So you're saying it's not a significant figure, but you're keeping it to reduce your rounding error later. But if this was your answer, and for what we're doing right now, this is your reportable answer. Now sometimes you'll see this grams over moles written that way, but another way to write that is grams times mole to the -1. So you might see that also, grams times moles to the -1. That just means that the negative means that the mole part is in a denominator, and the 1 part means it's only to the first power. So it's just another way of writing per mole. So when you see something like that, if you see it come across that in a textbook or something, that just means per mole. So just don't be confused by it. If you see this written out, it just means grams per 1 mole. Anyway, so this right here is how you calculate the molar mass portion of that. And we're going to take this and we're going to use it in the next part. The next part of the question, we take that a step further. So here, we're going to use our molar mass to do some conversions along with the procedure from the little chart that I pulled in right here. So the first one, I'm going to go from grams, so mass, and I'm going to moles. And then on the next one, I'm going to go from so many moles back to grams. So here you have your 20.50 grams of ethanol, CH3CH2OH, and I want to convert that to an equivalent number of moles of ethanol. So chemistry is done in moles, it's not actually done in grams, but you don't weigh in moles, you weigh in grams. So when you get the mass of something to figure out, you're trying to weigh out your proper number of moles, these conversions are done back and forth quite often. So if you wanted to see how many moles, if you had this many grams of ethanol, how many moles that would contribute to a chemical reaction, then we divide the mass by the molar mass of ethanol, which we just figured out was 46.07 grams of CH3CH2OH, and that's per 1 mole of CH3CH2OH. Now you should get in the habit of writing this out, because as these things get longer and you're piecing more of these together, it is going to be less and less recommended that like just doing it on a calculator is not quite enough. So if when you're doing these problems, of course you want to have a calculator handy. But you don't want to get in the habit of just typing stuff in on the calculator. Oftentimes, your instructor may require you to show this procedure, so you do need to learn it. You might say it's confusing me, but this is the procedural part of dimensional analysis, and you're actually showing how these units and factors work together. And so that you can cancel out the grams by starting out with grams in the top and putting the grams in the bottom, and that cancels out, and you're using that as a conversion factor to show, to end up in moles. So your grams cancel, now you're in moles. And then mathematically, if something's underneath something else, you divide. So to do this math, you multiply the things on the top, the numbers. So this is a 1, so you don't ever have to multiply by 1 because it still gives you that. And that's from your math class, identity property of multiplication. It works for division too. Multiplying or dividing by 1, you result in the same identity as what you started with. So this is just 20.50. That's 4 significant figures. That 0 is significant, or otherwise it would not have been written. And this 0 is significant because it comes between 2 non-zero digits. So this has 4 significant figures. This has 4 significant figures. So when you go to your calculator, you can give me an answer to 4 significant figures, which would look like this. If you rounded it to 4 sig figs, then this is how many moles of CH3CH2OH you would report as your answer. Excuse me. Now, on the other part, I've given a certain number of moles in the notes, and I want to know how many grams of ethanol that you would have. So this would be an example of if you figured out that a reaction was going to take as a reactant or produce as a product a certain number of moles of ethanol, and you wanted to figure out like how much that would be on the balance, what its mass would be. You would multiply the number of moles by the molar mass in grams per mole, which goes back to that little chart in the beginning. So this time you're starting in moles and you're going to go to grams. So you start off, you have your number of moles, and it's really funny how chemists take the word mole and they abbreviate it by just dropping the E. I don't know why, but that's just a convention. It's it's not much of a difference in writing out the actual word mole and then just having dropping one letter or putting the E on there. But anyway, this part you have your number of moles, so you're going to say, okay, 1 mole, we're going to work on canceling this out, of ethanol is equal to 46.07 grams of CH3CH2OH. Our moles cancel out. And now we're left in grams. So this time we do the same thing I told you up here. You multiply things across the top, and then you divide by the things that are in the bottom. So you don't ever have to divide by 1 because that doesn't change anything, but you do have to multiply those two numbers together. This has 3 significant figures. This has 4 significant figures. When you multiply or divide, you have to report your final answer rounded to the least number of total significant figures from either of your measurements. So this is 3 and that's 4, so we're going to round this off to 3. So we're going to do our math, and that's going to be 42.6 grams of ethanol. And again, it is extremely important that you write the units, the measurement, and what it is. That is a part that many students lose points for by not providing the proper unit or notation for their answers. So now we know how to convert from grams to moles based on a molar mass, and from moles to grams based on a molar mass. So we'll move forward. So we're going to go back to what our ethanol's molecular formula. So the molecular formula again is everything that's in there, every atom, and how many there are, every type of atom and how many of each one. And so that tells us a couple things. That a single ethanol molecule has the 2 carbon atoms, the 6 hydrogen atoms, and 1 oxygen atom. And that 1 mole of ethanol contains 2 moles of carbon atoms, 6 moles of hydrogen atoms, and 1 mole of oxygen atoms. So we end up with, basically conversion factors that we can use for other things. So when we're talking about our what all we can do with just having a formula, that's pretty powerful. So for instance, we can say that 1 CH3 CH2OH molecule, which means just 1 unit of the formula right there. Well, what we can say about that? Well, it has 2 carbon atoms. That's one thing that we can do. We can also say that also has, if we did the same thing, it has 6 hydrogen atoms. We can also say that it has 1 oxygen atom in 1 molecule. Now then we can also say that in addition to that, that 1 mole of ethanol, actually I think I'm going to maybe pick a different color for that. So I'm going to just back up just a little. I'm just going to change the color since I'm switching to moles. I'm just going to change my color of my pen, my ink. So 1 mole of CH3 CH2OH has 2 moles of carbon atoms. I can also say that with my 1 mole of ethanol, it has 6 moles of hydrogen atoms. And also I can say 1 mole of oxygen atoms. So this, that's still there, the top part of it. That is just a relationship that you can make. So if you needed to convert from moles of ethanol to moles of carbon atoms, you can use this as a conversion factor, because that's exactly how many moles of carbon atoms are in a mole of the formula units. Or if you're talking about just the individual molecule, each molecule has 2 carbon atoms in its formula. So those 2 kinds of conversion factors are also used periodically to solve problems in chemistry. So here, calculating the number of moles of each type of atom in a 20.50 gram ethanol sample. Well, if we can convert it to moles of ethanol like this, then we can convert to moles of each type of atom that we have. So the first step is you start out with your mass of ethanol. That's your starting point, your 20.50 grams of ethanol. So you have that as your starting point. Okay, so then you're going to convert to moles just like you did in the previous part of this problem. We have our molar mass of 46.07 grams of ethanol, and then we're going to convert that to moles by using that molar mass. So that gives us a mole of ethanol. Oops, that's a C. I don't like that. Looks not right. There we go. And then I cancel out my grams. I'm in moles. I say, okay, so 1 mole of this has 2 moles of that. So I want to put the 1 mole of ethanol, part of this conversion factor, in the bottom. 1 mole of CH3 CH2OH contains 2 moles of carbon atoms. And now I cancel out that with that, top and bottom. Okay, so if you do the calculation on that and round it to 4 significant digits, then you would approximate that at, looks like about 0.8900 if you calculate it. So those 2 zeros are part of my answer. It's where that last one rounded to. So then I would say moles of carbon atoms. That's probably a sufficient way to write that, and that's a reportable answer for that. Now, if you want to do, it says the moles of each type of atom, so we already know we have hydrogen and oxygen atoms in there. But the procedural part of this, since you're still doing it with the ethanol molecule here, converting the grams to moles, and then the 1 mole of ethanol containing however many moles of whatever the atoms are, then the only thing that really changes as far as numerically is this part right here, the number of moles, and this part right here, which type of atom it is. So really this stays the same, as you go through here. This all stays the same, right? And then this is what changes. So 6 moles of hydrogen atoms, that would change there. And then the next one would just only change there also. So procedurally, it looks the same all the way to this point where, to answer this question, 1 mole of oxygen atoms. So, then you can approximate your answer for each one of those. So let's say, for your hydrogen atoms, if you're counting your moles of hydrogen atoms, you end up with still four significant figures, and that becomes approximately 2.670 moles of hydrogen atoms. And then this one becomes 0.4550 moles of oxygen atoms to finish answering that question. So those become the rest of your reportable answer. So that will carry through that way as you do those kind of problems. Now, then, we might have to calculate representative particles in a particular amount of substance. So we have conversion factors for this. So we want to talk about, say, atoms and, let me say, molecules. So in other words, 1 mole of your ethanol, so CH3, CH2, OH. Well, if we're talking about particles, according to your little chart, that contains Avogadro's number of particles. So Avogadro's number of particles is 6.022 times 10 to the 23rd. And let's just say that this is a molecule. So 1 mole of ethanol contains Avogadro's number of ethanol molecules. So CH3, CH2, OH molecules. So that means that whole formula, when it's put together, CH3, CH2, OH, that is a molecule. So, structurally, that formula, you have, carbon atom, oxygen atom, and then, hydrogen atom off the oxygen. You end up with your, if you had a structural formula, it would kind of be like this, right? An actual structure. So this is the ethanol molecule, I guess you would say, in its structural kind of formula there. So this is a molecule. If you had a mole of ethanol, you would have 6.022 times 10 to the 23rd of these individual formulas, right? So that's how many would be in a mole. And we've already figured out that a mole of ethanol has a mass of 46.07 grams. So if you had 46.07 grams of ethanol, then you would have a mole of ethanol, which would mean that you would have this many ethanol molecules present. So it's kind of a weighing these things out, and by mass and converting to moles and then say to particles. That's kind of how a chemist would count molecules or atoms or formula units or whatever. So that's how we would count them, because you can't count to this number. So, and you can't see the atoms anyway, so individually like that. So you would have to weigh them out to be able to do that. But that's a conversion factor that you can use and should use quite a bit in this class. So another thing that you can look at as you're doing this is you have, if you're talking about individual atoms, then, a mole of anything is that many of those things. It's very comparable to when we say 1 dozen of something is 12 of those things. 1 dozen, 1 dozen roses is 12 roses. So that's the same thing as this, only with much larger numbers. So that's just a comparable thing, though. If you're talking about a dozen, well, we know what dozen means. Dozen means 12. Well, now we talk about moles. We talk about moles. That means Avogadro's number. So we're going to use those quite a bit. And if you look at your notes, so in your notes there are quite a few examples of these different types of, conversion factors that fall under this category. So I believe on the notes you have like 7 that I just gave you in that little section. So you want to look at those, and those are definitely usable for what you're doing. So now we're going to do an example of calculating the number of representative particles of each type in our 20.50 grams of ethanol sample. So if you're looking at your problem and you want to count the number of molecules, so let's just start with that one. So you have your 20.50 grams of your ethanol. So this again is starting out with just like it did before. So we're going to do exactly, the first part's going to be exactly the same. Before we can move on with this, we need to convert grams to moles. So if you go back to your little chart that was on the previous page, you're starting with mass, 20.50 grams, and I'm asking you to go to representative particles. In order to get there, you have to go through moles. So you first go to moles. So you're going to say, oh, okay, I know the molar mass of ethanol. I've already calculated it. It's 46.07 grams of ethanol is 1 mole of ethanol. So that part cancels out that part, and now you're in moles. And then once you're in moles, you follow your little diagram and you say, okay, to go from moles to particles, then I multiply by Avogadro's number. So this is where that comes in. So this would be molecules in this case, because I said we're going to start with molecules, and that's present in 1 mole of ethanol. And then you cancel out your moles. Now you're in molecules, which is a representative particle example that I told you earlier. So now you multiply the things on the top. Of course, you don't need to multiply or divide by 1. So you multiply the things across the top. You divide by the parts on the bottom. So when you do that, you end up with, you get 4 significant figures still. So this comes out to be 2.680 times 10 to the 23rd. So 10 to the 23rd power. And then that is CH3, CH2, OH molecules. So that part there gives you your answer. So for that kind of problem, you can just calculate your count, your number of molecules. If you had to determine the number of, say, a specific atom in there, so let's say I wanted to know how many, say, hydrogen atoms that I had in 20.50 gram. Not how many moles of them, but actually how many. So like a count. If I had to, mathematically calculate a count for the number of hydrogen atoms in 20.50 grams of ethanol. Well, it's going to start out pretty much like the same. Everything's going to start out the same part as here. But the thing is when you get to that part, we're going to also have to go back and see how many hydrogen atoms we had in a molecule. So we want to get to the actual number of hydrogen atoms. So the next part would be, if you had to calculate that, we're going to add one more step at the end. So as I write that out, you're going to see that it's going to be exactly the same all the way to here, and I'm going to add a step at the end. And that's again why I told you that it's a good practice to start keeping up with these. Okay, so don't want to leave any steps out, because later you think it's confusing with these steps right now. When these things get really long, and you don't have anything written in here, you can get lost really quick. So it's better to just go ahead and practice it and learn it this way. So I'm just going to carry this out one more time and show you the next step. Okay, so this is I'm just kind of copying where I've done so far. And as you're doing this, you're just checking your work and making sure that you're practicing good. You want to practice as perfectly as you can. They say that practice makes perfect, but I guess perfect practice actually makes perfect. You can practice incorrectly and it really doesn't matter sometimes. So we want to try to get as good as we can. So there's where I'm at right now, and I told you we were going to add just one more step. And where this is going to come from is on our previous part when we did like conversion factors. We're going to talk about if you have your molecule of ethanol, right? And I said hydrogen atoms. That was my, what I mentioned a second ago. Well, one CH3CH2OH, or ethanol molecule, right, has 6 hydrogen atoms in it. So now, since we know how to calculate how many molecules we have, then we should be able to actually calculate how many hydrogen atoms we have. And that just looks like this. So one molecule of CH3CH2OH, right, that part has 6 hydrogen atoms. So your molecules of ethanol go away and your atoms are left over. So really you just took this one more step, and then you just end up multiplying that by 6, which, if you round that to 4 significant figures, then you get, let's see, 1.608 times 10 to the 24, 10 to the 24th power hydrogen atoms. So that ends up being your mathematical answer. If you wanted to calculate your carbon atoms, then you could just, all this will be the same all the way to right here. And then this will just be 2 carbon atoms because it only has 2 per molecule. Or oxygen atoms, it contains 1 oxygen atom per molecule. So you just would change that number there, and that changes what factor that you multiply this by to get your final answer. So carrying out those procedures step by step is probably the best way to do that. So if you had any mass of ethanol, and the molar mass of ethanol in grams per mole, you can convert that, and then you can count your number of particles just by doing a calculation, and then you can extrapolate that to the number of individual atoms that you have in the measurement.